In the last lecture, we saw how we could start from the notion of metric spaces and arrive at the notion of topological spaces as a more general setting in which we can deal with the ideas of continuity. Just to remind you, a topological space is an ordered pair x, curly t, where x is a set and curly t is a subset of the power set of x, which means that curly t is a collection of subsets of x. Now this collection has to have certain restrictions, and the restrictions are the following. The null set and x must belong to this collection. An intersection of finite number of elements in curly t, that is, in this collection, must also be in curly t. Curly t is closed under arbitrary union as well. So, null set and x, the full set, belongs to the collection. The collection is closed under finite intersection and arbitrary union. Any collection of subsets which obey these properties is called a topology on X, and the elements of the topology, the subsets which obey these properties, are called open sets. Now the whole point of equipping a set X with this extra structure, the topology curly T, so that we land up with the notion of a topological space, was to be able to introduce the notion of continuity between two such spaces. And we saw that we can easily generalize the definition that we had for metric spaces in the following manner. Given two topological spaces x1 curly t1 and x2 curly t2, a function f from x1 to x2 is continuous if for all v belonging to curly t2, f inverse v belongs to curly t1. Note that v belonging to curly t2 is simply another way of saying that V is an open set in the second topological space. And similarly, F inverse V belongs to curly T1 is simply a way of saying F inverse V is an open set in the topological space X1, curly T1. So, if you take away the algebraic symbols and use just plain language, the definition of continuity simply becomes a function f is continuous if the inverse image of all open sets is open. This is something that we proved for a metric space, where we showed that this definition using the metric topology is equivalent to the epsilon delta definition, which involves metric functions. But let me remind you once again, on a topological space, you cannot derive this result from something else, because this now is a very definition of what continuity means. Now, for future reference, let me point out that very often, instead of saying topological space x, curly t, we will often say topological space x, where the topology curly t is just kept silent. This is legitimate, however, only if there is no scope for confusion. It may very well be possible that you have two different topologies, curly t1 and curly t2, on the same base set x. Then of course you will have to specify that the topological space is x, curly t1, or you are referring to the other topological space x, curly t2. In case you do not have scope for such confusion, it's often easier to just say topological space x. But you must always bear in mind that whenever you see the topological space, the set is just a part of the definition. It has to be equate with a topology in order to become a full-fledged topological space. So even if you don't mention it, the topology must always be there. Now, since topological spaces is basically the arena in which the game of continuity is being played, it is fitting, perhaps, that the equivalence between two topological spaces is essentially dictated by the existence of a special kind of continuous function, something called an homeomorphism. Let me define it now for you. Let x and y be topological spaces. Note that in writing this, I am already keeping individual topologies, curly Tx and curly Ty, for the two sets aside. I'm not saying that they are there, but they are of course there. Okay, let's begin again. Let X and Y be topological spaces and let F map from X to Y be a bijection. So it's 1 to 1 and onto. Therefore invertible. If both F and F inverse, which is a map of course from Y to X, are continuous functions, then F is called a homeomorphism. So a homeomorphism is a special kind of continuous function. It's invertible, and not only is it invertible, the inverse function is also continuous. Now, if you look at the definition of continuity, it should be easy to realize that a bijection F is a homeomorphism if it satisfies the statement that f of u is open if and only if u is open. To see that this is true, all you have to do is to realize that as far as f inverse is concerned, the inverse image of f inverse is basically f acting on a set, and using that you can easily see that our definition of continuity, coupled with the statement that f and f inverse are both continuous functions here, tell you that fu being open and u being open becomes equivalent if f is a homeomorphism. And if x and y have a homomorphism between them, that is, if a function f exists from x to y, which is a homeomorphism, then x and y are called homeomorphic. They are also called topologically equivalent. And the reason for that is pretty straightforward. As we have just seen, a homeomorphism establishes a bijective correspondence, not only between x and y, after all it is a bijective map between x and y, but also between their respective topologies. An open set in X maps onto an open set in Y and vice versa under F. Any property that can be expressed entirely in terms of the topology of X, which we call a topological property of X, will have a corresponding property for Y, which will just be mapped onto the previous property by the application of F. So the existence of a homeomorphism implies that whatever topological property you have on X will lead to a corresponding topological property on Y. All you have to do is apply F on the open sets of X, and whatever property you have in terms of that can directly be rewritten in terms of open sets of Y. And this is the reason why two sets which are homeomorphic are called topologically equivalent. And I will just leave you with a picture to think about this a bit. This is something we talked about in the very first lecture on topology. A very standard thing that people say is topology is a kind of geometry where you cannot distinguish a donut from a teacup. And the reason for that essentially is that you can continuously deform a donut into a teacup. The stages of that is being shown as you see the pictures going from left to right. But if you see them going from right to left, you will be able to figure out that there is an inverse transformation which maps the teacup also into the donut. And both of these maps are continuous. Therefore, there is a homeomorphism between a donut and a teacup, which is why we say, for a topologist, they are one and the same thing. We will next talk about the notion of a basis of a topological space. Now, the word basis may be very familiar to you, especially if you have studied in linear algebra. In a linear vector space, a basis is a collection of vectors which is special in the sense that you can find any vector in the space by forming a linear combination of these special vectors. And this helps us to make life very easy, especially where many properties of vector spaces are concerned, because very often, instead of having to deal with the entire vector space, which might very well have an infinite number of elements, you would have to deal with only the basis elements. And many results can be derived directly in terms of the basis elements themselves. A basis of a topological space is a similar concept. But in order to introduce this, let me go back to a familiar example of this basis that we have already seen, and that is the notion of open balls. Remember, in a metric topology, open balls play a very central role. Indeed, we defined open sets on a metric topology entirely in terms of open balls. An open set U in a metric space is one in which all points are interior points. That is, given any point X in U, there is an open ball centered at U that is contained within U. By the way, you should be able to realize that instead of saying that you have an open ball centered at X that is contained entirely within U, you could just as well have said you have an open ball which contains X somewhere in it, not necessarily at its center, which is contained entirely in U, and your definition would work perfectly well. Now, there is a theorem in metric topologies which is simply this. A set in a metric space is open if and only if it is a union of open balls. Well, let us see why this is true. Let's start with the assumption that U is a union of open balls. Now, open balls, as we have already seen earlier, are open sets in their own right. And we know that in any topology, and in particular we have proven this for the metric topology, that union of open sets is open. Therefore, U being a union of open balls is a union of open sets and hence is an open set. So, if U is a union of open balls, it is an open set. Let us now try to look at the converse. Let U be an open set. Now, what does this mean? It means that every point X in U is an interior point. That is, there is some positive radius, Rx, such that a ball of radius Rx centered at X is contained entirely within U. Now, for a given point X in U, there usually would be multiple such open balls which are contained entirely within U, each centered at X. Indeed, there would usually be infinitely many such open balls. But what matters is that there is at least one such open ball which contains X as its center and is contained entirely within U. So what we will do is for each X we will choose one such open ball centered at X and contained entirely in U. Now let us consider the union of all of these open balls as X runs over the entire open set. Now it's easy to see that because each of these open balls are contained within U, this union has to also be a subset of U. On the other hand, if you consider every X belonging to capital U, this X must belong to that one open ball which is centered at X, and therefore it belongs to the union. So every element of U is an element of this union, so this union contains U as one of its subsets. Therefore, this union is both a subset and a superset of U, and it must hence be equal to U. Therefore, an open set on a metric space must be a union of open balls. So, all open sets in a metric topology can be built out of open balls. And the collection of all open balls is definitely a smaller set than the collection of all open sets, that is, the topology on the metric space. So, it is natural to focus on this smaller collection since it should be able to tell you everything that you want to know about topological properties. Now, in particular, if you want to prove that a function f from a metric space M1 to another metric space M2 is continuous, it suffices to show that f inverse B is open in M1 for any open ball B in M2. You do not really have to look at all open sets. The proof of this is pretty straightforward. Every open set in M2, as we have just seen, is a union of open balls in M2, and therefore f inverse applied to an open set gives you union of f inverse applied to open balls, and if f inverse B is open in M1 for every B, then this follows rather trivially. Now, many properties of the topology in metric spaces can be discussed entirely in terms of the collection of all open balls rather than in terms of the collection of all its open sets, namely the metric topology itself. Now, this notion generalizes to the notion of a basis in a general topology. Now, let me first define what a basis of a topology is. If X is a set, a basis for topology T on X is a collection curly B of subsets of X, which are called the basis elements, with the following properties. Note that these elements of curly B are exactly the analog of open balls in metric spaces. The first property you demand of these elements is the following. Every element small x of capital X must belong to at least one of the basis elements. So for all small x belonging to capital X, there has to exist at least one capital B in curly B such that X is in capital B. And the second property that we demand essentially ensures that we can define a topology using just these basis elements. It goes as follows. If you take any two basis elements B1 and B2, then if X belongs to B1 intersection B2, then there exists another basis element B3 entirely inside this intersection, such that X is within this basis element. So we are not really saying here that the intersection of two basis elements is a basis element. Remember, if we are talking of just open balls, then the intersection of two open balls, namely this region, of course I am using R2, D2 as my topology here. It's easy to see that this region is not an open ball. However, if you take any point inside this region, you can put an open ball down that, which is entirely inside this intersection. Now, just like the open balls are the building block for open sets on a metric space, we would want the basis elements to be able to build up the topology on our space. So the important concept here is that of a topology generated by this basis curly B, which we have defined right now. So the topology curly T generated by curly B is defined as the collection of subsets of U of X, such that for every X belonging to U, there exists a basis element that is a set in curly B, such that X belongs to capital B, which is a subset of U. This particular basis element is contained entirely in the set U. So if you take all such subsets and call them your open sets, and hence the collection, the topology, you are actually going to end up with a well-defined proper topological space where capital X is of course the base set and curly T is a topology. Now of course we need to check whether this collection of subsets U defined in this manner actually satisfy all the properties of a topology or not. But before we go there, let me point out the close parallel between this definition and the properties of open balls that we know of in metric spaces. In a metric space, of course, you would call a particular set open only if all its points are interior points, which means that you will always find open balls which contain your point, and that those open balls must be completely contained within the set. You should see that this is exactly the same, except that we are doing this with arbitrary sets capital B belonging to a particular collection curly B, and not just specific open balls, which of course depends strongly on the metric function. Now, let us prove that curly T is actually a topology. Well, the first thing that you need in order to ensure that something is a topology is that it has to be a collection where the null set and the whole set, null and X, occur as elements. The null is in the collection trivially simply because in order to fail to be in this collection of subsets, we must find a point X belonging to the set for which no such basis element exists. But since null has no points at all, it is impossible for the null set to actually violate this condition, and therefore for the null set this statement that it is in the collection is true vacuously. Now, capital X on the other hand is definitely in the collection simply because of this basic property of a basis. Remember, if a collection of elements has to be a basis, then for every small x in capital X, there has to be a basis element which contains X. And thus, capital X is one of the subsets of capital X for which the condition that you can see on the top of your screen is definitely true. Now, the other important property the topology has to satisfy is that the topology has to be closed under arbitrary unions and under finite intersections. Now, given a family U alpha, which is indexed by some label alpha which belongs to a particular set, capital J. This J could be a finite or an infinite set, but it's an indexing set for this collection of elements of curly T. If you take the union of all such elements, that is union over all alpha in J of the U alphas, then you have to get an open set if curly T defined this way is going to be a topology. Now, to check whether that is true, let us take an arbitrary element X in this union. Now, if X belongs to this union, there must be some element in this collection, one of these sets U alpha, let's say U beta in particular, which contains X. So X must belong to at least one of these U alphas. Let's say it's U beta. Now U beta, being in our collection, must satisfy this property that there has to be a basis element capital B in curly B such that X is contained in capital B, which in turn is entirely within U beta. But of course, anything which is entirely contained in U beta is contained in the union of all the U alphas, which means the union is in our collection. Finally, we come to the issue of finite intersections of elements from this collection. In fact, I'm going to show this for only two such elements, U1 and U2, which satisfy this condition up here. It is very easy to extend this from two elements to any finite number of elements. I will leave that part of the argument to you. So, what we need to show is that if U1 and U2 belongs to this collection curly T, then U1 intersection U2 must also belong to this collection. How do you show that? You start by assuming that U1 intersection U2 is not empty. Because if U1 intersection U2 is empty, then as we have already argued, it trivially belongs to the collection. Because U1 intersection U2 is not empty, we will be able to find a point X in U1 intersection U2. Then, X must belong to both U1 and U2, and because X belongs to U1, there has to exist a basis element B1 such that X is inside B1 and B1 is contained entirely inside U1. Similarly, X belongs to U2 and therefore there has to exist a basis element B2 by hypothesis such that X belongs to B2 and B2 is contained entirely inside U2. Now, since X is in both B1 and B2, it must be in the intersection of B1 and B2. And this is exactly where the second defining property of a basis element, the one involving intersections, namely this one, comes into play. Note that what this property tells you is that if you take the intersection of two basis elements, then any point in that intersection will have a basis element containing it, and that basis element will be entirely within the intersection of B1 and B2. So going back to our current situation, our X is in B1 intersection B2. So according to the defining property, there has to be another element B3 in the basis, which is contained entirely inside B1 intersection B2, and not only that, which contains X. But since B1 intersection B2 is a subset of U1 intersection U2, what we have managed to prove is that given an intersection of any two elements of our collection, for any element in that intersection, there is a basis element, namely B3 here, which is contained entirely within this intersection and which contains as an element the point X. Now this is exactly our defining property for the collection that we are talking about, and hence, since we have been calling the elements of our collection open sets, what this implies is finite intersections of any two open sets are open, and of course what we have done is proven it for two elements, but frankly an extension to more than two but a finite number of such elements is rather trivial. Now we have enough under our belt to claim that curly T, this collection of sets, is actually a topology. Now we can also use an alternate way of speaking about the topology generated by a basis. This topology, curly T, is a collection of all unions of elements taken from curly B. Now the previous characterization of the topology generated by a basis must have been very familiar, at least should have looked very much like how we define open sets in a metric space, by essentially saying that all points are interior points. In a metric space, what we had said was, for each and every point in an open set, you must have an open ball which contains that element and which is contained entirely inside the set. Very similarly, here what we are saying is an open set is one for which every element corresponds to at least one basis element which contains that and is in turn contained in the set. Now, the alternative way of speaking about topologies in a metric space is simply by considering all possible unions of collections of open balls. And we have already seen before that that topology is essentially the same as the one which we define by saying that open sets are only those for which every point is an interior point. The equivalent statement for a general topological space is simply this: if curly B is a basis for topology curly T on X, then curly T is nothing but a collection of all unions of elements taken from curly B. I will leave the task of proving that this is a statement which is exactly equivalent to our previous characterization of a topology as an exercise for you. What we have seen is, given a basis curly B of subsets of X, which of course obeys the basic defining properties of a basis, we can construct a topology on X, which is generated by that basis. Now what about the converse of this statement? Given a topological space X, curly T, can I figure out a criterion which will tell me whether a collection of subsets of this set X is a basis for the topology curly T or not? And that is exactly what we are going to describe now. Given a topological space X and a topology curly T, suppose curly C is a collection of open sets of X, which of course means elements of curly T, such that for all U belonging to curly T, that is for all open sets, and for all X belonging to U, there must exist some subset of U, capital C, an element of curly C, such that X belongs to capital C. If this happens, then curly C is a basis for the topology curly T on X. In other words, you have to take a collection of elements from the topology which is big enough to sort of cover every element which belongs to an open set. Whenever you take an element X from an open set U, you should be able to find an element in your collection curly C which will be contained entirely inside U and which will contain X itself. Now, we need to do two things here to establish that this is correct. First of all, we need to establish that this collection curly C is actually a basis. That is, it satisfies all the properties that a basis should have. And once we have established that curly C is a basis, what we need to show is that the topology that is generated by curly C is the same as the topology curly T that we started with. So now for the first part of the proof, that curly C is a basis. The first thing that you need to show is that for every element small x of capital X, there must exist an element in our collection curly C, some set capital C, which will contain X as an element, and this is trivial since capital X itself is in the topology, and by hypothesis here, for all X belonging to capital X, remember this works for all elements of the topology, I can take capital X itself as U here, and then this part simply reads, for all X belonging to capital X, there must exist a capital C belonging to curly C, such that X belongs to capital C and which is itself contained by capital X. So the first property of a basis is trivially satisfied here by the hypothesis that we have made about curly C. Now what about the intersection of any two elements of curly C? So if we take two elements C1 and C2 from curly C, and if X is an element of C1 intersection C2, note once again that if C1 intersection C2 is null, then it's vacuously open, so we don't really have to worry about that. If it is not null, there will be elements X in C1 intersection C2. We consider any such element. We have to show that there exists C3 in the collection such that X is an element of C3 and X C3 is contained inside the intersection. This of course is the second defining property of a basis. To figure this out, let's start with the statement that C1 intersection C2 is not empty and X belongs to that. Since C1 and C2 are open sets, so is C1 intersection C2. Remember, these C1 and C2 elements are actually elements which are taken from the topology itself, so they are all open sets. Now, of course, C1 intersection C2 is an intersection of two open sets, so it is open, but it is not necessarily in my collection curly C. But because C1 intersection C2 is open, according to the hypothesis, there has to be an element C3 contained in curly C such that X is an element of C3 and that is a subset of C1 intersection C2. So, our second defining property of the basis is also established. So, we now turn to the other half of the problem, which is to show that the topology generated by curly C, which I am going to call curly T prime for the time being, is exactly the same as the topology curly T that we started out with. To show this, we first start by considering the case where U is an element of our topology curly T. Now, if X is a point belonging to U, then by our hypothesis, there is an element in the collection curly C, let's call that C of X, such that X belongs to C of X and which of course in turn is completely contained in U. Now, of course, for a given small x, there may be multiple elements of the collection curly C which contains it and which satisfies this condition, but we are going to pick one Cx for every x. Note that the hypothesis guarantees that for every x there is at least one such Cx. So if I take the union of all of these Cx's, it's pretty easy to see that that exactly is the same as the set U. This exactly parallels the argument that we had given earlier for open sets in metric spaces, so I'm not going to go into the details of that argument all over again. Note that curly T prime, the topology generated by curly C, is nothing but the collection of all unions of elements taken from curly C, which, as we have already established, is a genuine basis. And since our U is nothing but a union of all such sets C of X, it must be an element of curly T prime. So every element of our original topology must belong to the topology generated by curly C. In other words, our topology must be a subset of curly T prime, the topology generated by curly C. All we need to do is that the inclusion works the other way around as well. Curly T prime is also a subset of curly T. And that will help us to establish that curly T and curly T prime are exactly the same. To show this, we start by considering an element W which belongs to curly T prime. Now, by definition of the topology generated by curly C, W must be a union of elements of curly C. But curly C, remember, is a subset of curly T. We have taken the elements of curly C from among the open sets, and curly T is closed under arbitrary union. So W, which is a union of elements of curly C, is a union of open sets in our original topology. So W must also be an open set. In other words, W must belong to curly T. So every element of curly T prime must be an element of curly T, and this completes our proof that curly T prime is a subset of curly T. We have already shown that curly T is a subset of curly T prime, and therefore the topology generated by this curly C and the original topology curly T must be one and the same. By now, we have spent quite a long time in this lecture discussing properties of bases of topologies. At the very outset, I have said that the reason why we want to look at the basis for a particular topology is because it would give us a smaller collection in general than the whole topology itself, and much of what we want to do with the full topology can be understood entirely in terms of just the basis sets. One obvious place where this will be very useful is in the definition of continuity of functions. So, if X and Y are two topological spaces, and if the topology on Y is generated by a particular basis curly B, then in order to show that a function f which maps X into Y is continuous, all you really need to show is the following. Instead of having to show that all open sets in Y have pre-images or inverse images which are open in X, all you have to do is take every basis element, that is element of curly B, in this case I have taken an element capital B, and apply F inverse on that. If F inverse capital B is open for each and every element in the basis, then our function is continuous. Now the proof of this is trivial, since every open set V, which is a subset of Y, is already known to be a union of collection of elements from curly B. V is a union of capital B alpha, where alpha is taken from some indexing set J. And it's very easy task in set theory to prove that when you apply F inverse on capital V, that is F inverse on this union, then the result is the union over all alpha of F inverse B alpha. Now, I've already assumed that this holds. That is, F inverse capital B is open for all basis elements. But if that happens, F inverse B alpha is definitely open, and this is a union of an arbitrary collection of open sets. And by the basic definition of topology, this must be open. So what we have shown is that if you can show that F inverse B is open for all B belonging to curly B, then F inverse V for every open set is open in X, and hence F is continuous according to our definition of continuity. The converse of this, that is, if a function is continuous, then F inverse B is open for all B belonging to curly B, is really rather trivial, because every element of curly B has to be an open set by the way a basis is constructed. So if the inverse image of all open sets is open, that was our original definition of continuity, then the inverse image of every basis element has to be open. So this shows that instead of worrying about the entire collection of open sets in Y, you just have to look at the basis elements and what are their pre-images under the function F. Now this advantage is not the only reason why we want to look at basis. There are many other applications of basis for topologies, and we are going to meet a few as we go along. But before we explore these applications, let me introduce at least one new topology which is described in terms of its basis. Now we already have examples of topologies described by basis. In particular, all metric topologies have been defined in terms of their basis, that is, in terms of the collection of open balls. So the standard topology in R, of course, is no exception. There, the set of all open intervals A, B is a basis. Of course, these are nothing but collections of all points X which satisfy the inequality A is less than X less than B, and these are nothing but open balls if you are using the standard metric on the real line given by d of x, y equals mod of x minus y. Now, this is not the only topology one can have on R. A very important topology, especially one which allows us to sort of look at many concepts more clearly, is the so-called lower limit topology. And we are going to describe that in terms of its basis. For this, we consider a collection of all semi-open intervals of the form A, B, but here it's closed at A, in the sense that we are considering those points X or collections of those points X belonging to the real line which obey the inequality A is less than or equal to X, which in turn is less than B. So the point A is included in the interval, the point B isn't. Now what I'm going to claim is that this collection is a basis on R. Now to check that this is a basis, what we need to do is, of course, prove that the basic properties of a basis work here. Now, every point X of our set, in this case R, the real line, has to be inside a basis element. Now that is sort of easy to see. After all, X, if nowhere else, is inside the semi-open interval stretching from X to Y, where Y is of course more than X, in order to ensure that this is a real non-null interval, and X belongs there. So there are of course elements in this collection to which any arbitrary point X in R belongs. Now what about the intersection demand on basis? Remember, the intersection demand is that if you take two basis elements, every point in the intersection of these two basis elements must have a basis element which contains that point and which is entirely inside that intersection. Now, of course, what you can have is a situation like this where you have two semi-open intervals x1 to y1 and x2 to y2 which are completely disjoint. In that case, their intersection of course is null. And if the intersection is null, then the intersection is trivially a member of the basis. So we don't really worry about that. But the other option would be that the intersection is itself a semi-open interval. I have shown one example where x1 is less than x2, which in turn is less than y1 and which is in turn is less than y2. You can think of other possible permutations of the orders here, but as long as there is an overlap, it's pretty clear the overlap has to be a semi-open interval itself. So to figure out a basis element which contains a point in this overlap, you don't really have to look further. The intersection itself is a basis element which will be entirely contained inside the intersection, so to speak. And therefore, the second demand for basis elements is also satisfied here. So now that we have seen that this collection is a basis, it follows that you can have a topology which this basis generates. And the important point is that this actually generates a new topology, a topology which is distinct from the previous one. It's called the so-called lower limit topology, denoted by RL. When we just say the topology R, we of course mean that the underlying set is the real line, and the topology or the collection of open sets is the one which is given by the standard metric topology on R, or our original topology that we started out with. When we say the topology is RL, we of course mean that the underlying set is still R, but the topology, the collection of open sets on this particular topological space, is different. In particular, let's take a look at this example. The semi-open interval A, B is an open set in RL. That's by definition, it's a basis element, so it has to be an open set. But this obviously is not an open set in R. In particular, the point A at the edge is not an interior point in the standard topology of R, simply because if you take any open interval surrounding the point A, it has to stick outside this A, B interval. On the other hand, A, B is an open set in both topologies. Now, this is not a surprise when it comes to R. And let me stress once again, when I just say R, I mean R with the standard topology. But let us try to convince ourselves that this is also an open set in RL. To understand this, let's take a look at an arbitrary point X in this open interval A to B. Then of course, X is somewhere in between A and B. It's more than A and less than B. And we can always consider this particular semi-open interval. This is an semi-open interval for which the left end is actually the average of A and X. So it's less than X, more than A. And the right end here is the average of B and X. So it's more than X, less than B. It's obvious that X is in this semi-open interval, and it's also obvious that this semi-open interval is contained within the open interval A, B. So this shows that for all points inside A, B, there exists a basis element, in this case this semi-open interval, which contains that point and which is inside the interval A, B. That is why A, B is an open set in the topology where the basis elements are given by semi-open intervals. Indeed, if you wanted to prove formally that this is an open set in R, you would actually use a very similar proof. All you would do is consider an identical but now open interval between A plus X by 2 to B plus X by 2 and just repeat this argument. Anyway, we have established that A, B is an open set in both of these topologies. Now, the fact that there are different open sets in RL, these open sets, semi-open intervals, which are not contained in the topology of R, shows that these two topologies are different. So RL, despite sharing the same underlying set with R, namely the real line, is not homeomorphic to it. In fact, now that we have the lower limit topology defined for us, it is perhaps time to answer a question which may have risen in your minds when we were defining homeomorphism a while ago. We defined a homeomorphism as a continuous bijection whose inverse is also continuous. However, many of you may have wondered that if a bijection is continuous, shouldn't its inverse also be continuous automatically? So let me show you an example where this is really not true. Now consider this function, which is the identity function from RL to R. Of course, being the identity function, what it does is that it maps x to x. This is obviously a bijection. And its inverse, of course, is also the identity function, but this time from R to RL. Note that because the underlying sets are the same in the two cases, these two functions are exactly identical functions. However, continuity is a matter not only about the function, but really about the topologies that you have on the domain and the range. So we have to be a bit careful in deciding whether these functions are continuous or not. Now, to decide on whether this function is continuous or not, we can, of course, look only at the basis of the two topologies involved, in particular the basis of the topology of the range. In this case, a basis element of the range here is simply an open interval from A to B. And if you apply F inverse on that, which remember is exactly the same function as F, what you get is the same open interval A comma B. Now, note that while A comma B is a basis element of R, not just an open element set, but also a basis element, this is actually also open in RL, something we have just proven. So the inverse image of every basis element on the range of this function is an open function in the domain, and therefore this function f, the identity map between RL and R, is a continuous function. So here we have an example of a continuous bijection. But is its inverse also continuous? Let's take a look. The F inverse, of course, is a map from R to RL, as I said, and it just does the same job as F does. It maps x to x. Now, what about the way in which basis elements inverse map under this particular map? So, we are going to look at basis elements of the range RL, which are, of course, semi-open intervals. When G inverse acts on that, it gives you exactly the same semi-open interval. No surprises there. But now notice that while this semi-open interval is an open set in RL, not only that, it's a basis element of RL, the resulting object here is not open in R. So F inverse, despite being exactly the same map as F, is not a continuous map. So here you see two things. Firstly, the importance of the topology in deciding whether a function is continuous or not. And secondly, the fact that you can have continuous bijections which are not homeomorphisms. Of course, we already know that there can be no homeomorphism between RL and R simply because we have seen that they have different topologies. So it should not really come as a surprise that even the identity map is not a homeomorphism. Let us now return to the issue of other applications of the concept of basis. Right now, we are going to take a look at an example where the notion of a basis becomes very, very important. It is a process by which you can create larger topological spaces out of smaller ones. But before we go there, do we at all have examples of topological spaces to play with? Of course we have. The real line with this modulus function is definitely an example of a metric space and hence a topological space. Indeed, all metric spaces are examples of topological spaces, the metric topologies, and we have already seen at the end of the last lecture that there are topologies which are not metrizable, that is, which cannot be written as metric spaces for some choice of metric. So we have plenty of examples to play with. But now we come to a question. Given two topologies can we combine them together to form a bigger topology? And the basis of these two topologies will play a very important role in the construction. What I am going to describe to you now is a so-called product topology. Now, given the underlying sets X and Y of two topological spaces, it's pretty easy to form a bigger set, that is the Cartesian product X cross Y. Let me remind you that X cross Y, by definition, is a set formed by pairs of elements X, Y, where small x comes from capital X and small y comes from capital Y. A purely set theoretical definition of what is called a Cartesian product of two sets. Now, on this Cartesian product, we can define this so-called product topology, and it is defined as a topology that has as basis curly B all sets of the form U cross V, where U and V are open sets of X and Y respectively. Now, the first question that we should ask ourselves is this a genuine basis top? Now, remember, our curly B has all sets of the form U cross V. So, in particular, has X cross Y as a member. And therefore, the statement that there is a basis element containing small x for all x in X cross Y is trivial. After all, X cross Y itself is in the collection. It's slightly more non-trivial to prove the second property, but that also is pretty simple. Any two basis elements B1 and B2 must be of the form U1 cross V1 and U2 cross V2. Then, the intersection of B1 and B2, that is the intersection of these two Cartesian products, can be easily shown, and this is again a very familiar set theoretical property. If you do not know this already, you should actually try to prove it for yourself, that this intersection of direct products is actually a direct product of the individual intersections U1 intersection U2, direct producted with V1 intersection V2. Now, given the fact that U1 and U2 are open sets in capital X and V1 and V2 are open sets in capital Y, U1 intersection U2 is an open set in capital X, standard property of a topology. Similarly, V1 intersection V2 is an open set on capital Y, and hence this is a direct product of two open sets of X and Y respectively, and therefore it's a member, this collection that we are talking about. So curly B is a genuine basis. Notice that we have defined the topology on a product space by giving its basis rather than giving a full description of all the open sets in the product topology. However, we have already seen that if you are given a basis for a topology, the basis uniquely defines the corresponding topology. So this is perfectly alright. Indeed, you can actually economize further. Instead of saying that you have a basis which is formed by taking all possible direct products of open sets of the two spaces, you could just actually start with the basis curly B of the topology on X and curly C for that in Y, and define curly D to be the collection of all Cartesian products B cross C, where capital B belongs to curly B and capital C belongs to curly C. It turns out that this curly D is also a basis for the product topology on the Cartesian product X cross Y. The topology you get by taking just this curly D, where you take the Cartesian products of only basis elements of X and Y, is the same as the topology that you get when you take this much bigger basis that we started out with, the basis formed by collecting together all Cartesian products of open sets of X and Y. I will leave the proof of this as an exercise. We will see plenty of examples of product topologies as we go along, but at this stage, let me just point out one. Now, This is a very simple example where the direct product or the Cartesian product set that we are talking about is simply R cross R, the Cartesian product of the real line with itself, and all its elements by definition are pairs x comma y, where x is an element of R and y is also an element of the second R. So basically, pairs of real numbers. Now we already know what this set is. This is a set R2, which is equivalent to all points in a plane. And it turns out that the product topology of R cross R is exactly the same as a standard Euclidean topology that we define on R2. That was a bit of a loose statement, because after all, the product topology depends on exactly what topologies you are using on the individual sets that you start out with. Here we have assumed, without even mentioning it, that the topology that I am going to use on R is a standard topology on the real line, the topology where a possible basis is a set of all open intervals. The statement that I have made about R cross R having the same topology as the Euclidean metric topology is actually something which follows once you adopt the standard topology on R. Here is an illustration of that statement. If you take two basis elements, the green one is a basis element of the topology on this R, and the blue one is a basis element of the topology on this R, and form their Cartesian product, what I get is this rectangle. And this rectangle is going to be a basis element for R2. You should be able to convince yourselves that if you take a collection of all such rectangles, that provides a genuine basis for the topology on R2, which the Euclidean metric would give you. At this point, it may be a good idea to stress that the direct product of basis elements of the two topologies which go into a product topology gives you a basis element for the product topology, but not necessarily all its open sets. For example, if you take a look at this particular open set here, on R2, it's obviously an open set, but it's not a direct product of two basis elements. Once again, the importance of basis elements comes into view. You are defining the product topology, remember, using basis elements rather than by specifying all its open sets in one go. Now there are lots of other ways in which you can get new topologies from older ones. We will explore some of those in the next lecture.